In this video, we will say what is a group. After all, this series of videos is called group theory, even though the examples and applications described here are mainly useful for chemists. This video has 3 parts. In the first part, we will talk about the definition of a group. In the second, I will briefly mention subgroups. And in the last, I will mention the difference between point groups and space groups. So, let's start. The definition of a group is as follows. A group is some set G, along with a binary operation that conforms to 4 axioms. Here are some examples of a set. It can be a set of numbers. In this particular case, we have set of integers, set of functions, set of matrices, or, for instance, set of symmetry operations. These particular symmetry operations make up C3D point group. For instance, ammonia has symmetry that is described by C3D point group. Also, please observe that a set can have finite or infinite number of elements. What about the binary operation? Binary operation means that you take 2 elements from the set and combine them in some well-defined way. Generic symbol for binary operation is a dot. Binary operation could be, for instance, just simply addition. If elements are functions, then we could take, for instance, a composite of the functions. What is the binary operation associated with the symmetry elements? It's just the action of performing one operation one after the other, so it's very trivial. We will do a few examples now, only to make you familiar with a certain formalism. So here we see PF5, the symmetry elements are drawn, the labeling is very easy, C2'1 goes through F1, and sigma V1 also goes through F1. So I am sure that you get the pattern. I personally prefer drawing only the top projection, and then I remember if the atoms on the top and bottom change or not. Let's do C2'1. Notice the top and bottom atoms have swapped. Then we do sigma V1. Sigma V doesn't do another swap, so the overall effect of the 2 operations is that of sigma H. Top and bottom swapped, and the equatorial atoms return to the initial positions. Carrying out 2 or more symmetry operations is represented algebraically as multiplication. By convention, the first operation is written at the right, and that is a common thing in math. For instance, in calculus, this symbol implies that differentiation with respect to y is to be carried out first. For this particular example, if you do the operations in a reverse order, then you get the same result. And by the way, it would be good if you could do that by yourself. So in this case, the multiplication is said to be commutative, that is, the 2 operations C2'1 and sigma V1 commute. But that is not the rule. Here we see more examples, and please look at the highlighted operations. For instance, in these instances, the order does matter. So we say that overall, for D3H, the order matters, and we say that this group is non-abelian. But there are some groups where the order of operations doesn't matter, and these groups are called abelian. One example can be, for instance, C2V. Here I just drew out the highlighted examples to show you that the results are indeed different. Be careful. Here, for instance, we see C2,3 going through atom F1. That is, we keep the position of symmetry elements according to the initial configuration. So let's do some ternary operation. The rule is exactly the same. We just keep going from right to left. So here are just a couple of examples so that we can practice, and in a couple of seconds I'm going to show you the answer. Coming back to definition of groups, set and binary operation is not enough. On top of that, 4 conditions need to be fulfilled. First is closure. I used a bit of mathematical notation because I feel it's more precise, but feel free to ignore it. Basically, closure means that combining any 2 elements of the set gives another element of the set. So let's say we have this finite set of numbers and the binary operation is addition. Can this be a group? Well, 1 plus 5 is 6, but for instance, 5 plus 6 is 11. 11 is not the element of the set, so no, this cannot be a group. We don't need to even look at other requirements. The first is not met, so this set under addition doesn't form a group. So let's look at this first example from the table. We can see that it does fulfill the first condition, because when we add any 2 integers, it will give us an integer which is also in the group. Now, for examples 2 to 4, we need to put some effort to show the closure. So common strategy is to construct so-called Cayley table. It's basically like a multiplication table. I left one of the tables unfinished, so you can play with it if you want to. Let's move on to the second requirement, the presence of the identity element. When you combine any element of the set, say x, with the identity element, which is also in the set, it gives you back x. You can notice that the identity element commutes with every other element, that is, the order doesn't matter. Okay, so let's go through the examples in a table. First example, the identity element will be 0, because adding 0 leaves the element that we were adding to unchanged. The second example is with function composition. Just ignore it if you're not familiar with it. If you are, then the identity element is of course f of x equals x. Then the matrices, the identity element is obviously the identity matrix, which always leaves the other matrix unchanged when you multiply one by the other. And then finally, the last example, identity element is the identity operation. Next requirement is the presence of inversion. Every element from the set must have an inverse element which does the exact opposite, such that when we perform the binary operation on these elements, it gives you the identity element. Let's walk through the table once again. So first example with integers. Could you point out an inverse to -4? I'm sure you got it. It's 4, because when we perform the binary operation, then -4 plus 4 equals 0. Posh but simple. Next example, the inverse are quite obvious. Inverse of f of x equals x is 1 over x. Basically, you just flip over the formula upside down. These functions are 1-to-1 and onto, so it's all sweet. Notice that we have to take away a 0 and 1 from the domain and codomain, just saying. Anyway, then the example with matrices. Here's the formula for inverse, and if you want to, you can calculate to your heart content, but you could also look at the Cayley table and see where we ended up with the identity element. So we can see that the inverse of C1 is C2, the inverse of C2 is C1. For S elements, they themselves are their own inverse. So for instance, inverse of S1 is S1. The last requirement is associativity. So if X, Y, and Z elements are in the set, then doesn't matter how you put brackets, you get the same answer. This is very easy to see in the first example with integers. No matter how you add 3 or more numbers, we will always get the same answer. However, please be a bit careful. Yes, with addition we can add even back to front, but associativity specifically refers to the presence of brackets, and with symmetry operations we cannot do operations back to front and however we like if a group is non-abelian. So let's look at this example. The molecule is PF5 and the labeling of symmetry elements is the same as before. So here the brackets don't change the normal right to left flow. First C22 and then sigma V1. So that gives overall S35. But that doesn't really matter because we can just immediately do sigma H and the overall effect is that of C32. Now the brackets do influence the order. First we do sigma V1, then sigma H, which yields in C21. And please be careful, we need to do C22 first, so we need to go back to the starting configuration, do C22, and then we can do C21. Notice that if we did these two C2 operations in a reverse order, we would end up with a different result, because D3H is non-abelian as we already mentioned. I'm not going to show you the associative property for examples 2 to 4 because, guess what, we would have to do the Cayley table. And I'm not going to do that, I have enough Cayley tables for today. Speaking of Cayley tables, I would like to show you again the Cayley table which I introduced to you when we talked about closure. Notice that the table for symmetry operations has exactly the same pattern as the one for the matrices. Yes, I chosen the matrices carefully and even labeled them in a very suggestive way. This means that there is a correspondence between these two groups. That also suggests that we might be able to encapsulate informations about symmetry operation in matrices. These particular matrices are for irreducible representation in C3V group. We will construct them in a couple of videos, but for the moment just simply take note of that. To close off with Cayley tables, let's do this particular example. The first operation comes from the row and the second from the column. The overall effect is that of sigma V2. If we do the same with matrices, we get S3, and we would expect S2. But these two entries are placed symmetrically with respect to the diagonal. So if we make matrices swap place, then we get indeed S2. It just depends which matrix we regard as first. Also notice that we do operations from right to left, but matrix multiplication from left to right. But the correlation exists, the groups are isomorphic, if you want to know the proper name for it. The next thing I want to mention are subgroups. We already know that water is C2V, it has two sigma V's, C2 and E. Now please look at this C4V molecule and notice that it has the same symmetry elements plus couple more. So we say that C2V is a subgroup of C4V. You might occasionally find it helpful. Here we have staggered ferrocene with some chlorine substituents. If chlorines were not there, then the group would be just D5D. The presence of chlorines reduces the symmetry. So what group is it? To assign symmetry faster, you may go to the website, and below the character table there is a list of subgroups, and you can see that C2H is a subgroup of D5D, and indeed that is the group of the molecule that we are interested in. The last thing I want to mention is what point group means and how does it differ from a space group. Chemists use mainly two types of groups. There are point groups that deal with finite molecules, and that's what this series of videos is about, and space groups, which are used to deal with effectively infinite arrays of molecules and ions. So space groups have applications in crystallography. The main difference between point group and space group is that for space group, translational symmetry is allowed. and that moves all the points associated with the molecules or ions in space. In contrast, for point groups, translational symmetry is not allowed, and performing any symmetry operation on any finite molecule results in at least one point in a molecule remaining unshifted. This point does not need to be situated at the atom. Think for instance about a point of inversion in staggered ethane. So that's everything I have for you today. I hope it helps. Thank you for watching. Bye!